Welcome to this comprehensive guide on the Task Parallel Library, or TPL, specifically designed for beginners looking to significantly enhance their application's performance and responsiveness. We will explore how TPL can revolutionize your approach to concurrent programming in .NET. The Task Parallel Library is a powerful and integral set of APIs within the .NET framework, meticulously crafted to simplify the seamless integration of parallelism and concurrency directly into your applications. It provides a higher-level abstraction over traditional threading mechanisms. It empowers developers to effortlessly write code that executes multiple tasks simultaneously, effectively leveraging the full potential of modern multi-core processors. This capability is crucial for improving application responsiveness and throughput, especially in computationally intensive scenarios. TPL primarily resides in the system, threading, tasks namespace, abstracting away the often complex and error-prone details of thread management, intricate task scheduling, and efficient load balancing. This abstraction allows for a much cleaner and more maintainable codebase. This powerful abstraction allows developers to focus more intently on core application logic and less on the intricate, low-level threading details, thereby significantly boosting overall development productivity and reducing the potential for concurrency bugs. It simplifies the development of robust, scalable applications. Let's now delve deeper into the fundamental core concepts that form the robust foundation of the Task Parallel Library. Understanding these concepts is key to effectively utilizing TPL in your projects. Tasks are the fundamental units of work in TPL, representing asynchronous operations that are lightweight, highly flexible, and can be easily chained together or awaited. Unlike traditional threads, tasks are managed by the TPL scheduler, optimizing resource usage. The Parallel class offers essential methods such as parallel, for, and parallel.forEach for executing loops concurrently, intelligently distributing iterations across multiple available processors. This significantly speeds up operations that involve iterating over large collections or performing repetitive calculations. Task schedulers are crucial components responsible for managing and executing tasks, determining precisely how and when they are scheduled to run on available threads. They play a vital role in optimizing resource utilization and ensuring efficient task execution. The default task scheduler is built upon the robust and highly optimized .NET thread pool, ensuring efficient resource utilization by reusing threads rather than constantly creating and destroying them. This design minimizes overhead and maximizes performance. The TPL Dataflow library, found in the system, threading, tasks, Dataflow namespace, provides specialized components for message passing and efficiently parallelizing both CPU-intensive and I/O-intensive applications. It enables the creation of powerful, asynchronous data pipelines. Now, let's explore the significant and tangible benefits of incorporating the Task Parallel Library into your development workflow. These advantages extend beyond just performance, impacting code quality and developer productivity. TPL dramatically enhances efficiency by fully utilizing multi-core processors, thereby reducing the significant overhead traditionally associated with manual thread creation and destruction. This leads to faster execution times and more responsive applications. It significantly improves scalability by effectively managing and scheduling tasks across various threads, which is absolutely crucial for applications requiring robust concurrent processing. As workloads increase, TPL helps maintain performance by distributing work efficiently. TPL offers a higher level of abstraction, streamlining code development and maintenance for complex asynchronous operations. This means less boilerplate code and a clearer understanding of the program's flow, even with parallel execution. Its intuitive abstractions simplify parallel programming, allowing developers to avoid the inherent complexities and potential pitfalls of manual thread management. This makes parallel programming accessible to a wider range of developers. This means developers can concentrate more on core application logic and business requirements, leading to increased productivity, faster development cycles, and ultimately, higher quality software. It shifts the focus from managing threads to solving problems. Next, we'll explore the key features and powerful APIs that make TPL so versatile and indispensable for modern .NET development. These tools provide the building blocks for concurrent applications. Task Run executes a delegate on a thread pool thread, providing a simple and efficient way to offload work from the main thread, preventing UI freezes and improving application responsiveness. It's often the first choice for simple background operations. Task Factory to Start New offers more granular control over task creation options, allowing for advanced scenarios such as specifying task creation flags or custom schedulers. While Task Run is often preferred for simplicity, Start New provides deeper customization. For parallel loops, Parallel for executes a traditional for loop concurrently, while Parallel.forEach does the same for each loops, enabling efficient processing of collections in parallel. Both methods automatically manage thread allocation and workload distribution. Parallel Invoke allows you to execute a set of independent actions simultaneously, making it perfect for scenarios where multiple unrelated tasks can run in parallel without dependencies. This can significantly reduce overall execution time for such operations. Task continuations, using continuewith, enable you to specify a task to run immediately after another completes, fails, or is canceled, allowing for the construction of complex and robust asynchronous workflows. This provides powerful control over task sequencing. Cancellation token source and cancellation token provide a cooperative mechanism for gracefully canceling tasks, allowing long-running operations to be stopped in an orderly fashion without abrupt termination. This is crucial for responsive applications and resource management. For exception handling in parallel tasks, aggregate exception is specifically used to manage multiple exceptions that might arise from various parallel tasks, consolidating them into a single, manageable exception. This simplifies error reporting and recovery in concurrent code. Now, let's see how TPL integrates seamlessly and powerfully within the Visual Studio development environment, providing developers with robust tools for building and debugging parallel applications. Visual Studio offers robust and specialized tools for debugging and profiling parallel code, making the development process much smoother and more efficient. Features like the Parallel Stacks window provide invaluable insights into concurrent execution. You can attach to multiple threads, trace parallel executions, and monitor task status directly within the integrated development environment, providing a comprehensive view of your application's concurrent behavior. This greatly aids in identifying and resolving concurrency issues. Next, we'll explore TPL's application and considerations within the Unity 3D engine, a popular platform for game development. While Unity has its own concurrency patterns, TPL can still play a role. While Unity 3D primarily supports C# 3.5 and its own coroutine system, the task parallel library can still be effectively utilized for background processing that doesn't directly interact with Unity's main thread APIs. This allows for offloading heavy computations. Unity leverages the yield instruction to simulate multi-threading using coroutines, which is a common and effective pattern for asynchronous operations within the game engine. Coroutines are managed by Unity's main thread and are suitable for many in-game asynchronous tasks. However, it's crucial to remember that Unity's API relating to game objects, components, and scene management can only be accessed from the main thread. Attempting to modify these from a TPL task will result in errors and crashes, requiring careful synchronization. For highly multi-threaded and performant code, especially in data-oriented design, the Unity job system is an excellent alternative, though it has strict data type requirements and a different programming model. It's designed for maximum performance on multi-core processors. To maximize TPL's benefits and ensure robust, high-performing applications, adhering to established best practices is absolutely essential. These guidelines help avoid common pitfalls and optimize your concurrent code. It's important to strike a balance between fine-grained and coarse-grained tasks to avoid excessive overhead from too many small tasks or reduced parallelism from too few large tasks. Optimal task sizing is key for efficient execution. Avoid oversubscription by not creating more tasks than available CPU cores, as this can lead to unnecessary context switching and thread contention, ultimately degrading performance rather than improving it. Monitor your CPU utilization carefully. Always handle exceptions properly using try-catch blocks or by inspecting tasks. Exception to prevent application crashes and ensure graceful error recovery in your parallel operations. Unhandled exceptions and tasks can bring down your entire application. Regularly check task status using properties like task.isFaulted, task.isCompleted, and task.isCancelled to monitor task health and react appropriately to different completion states. This allows for robust control flow in asynchronous operations. Combining async/await with TPL simplifies asynchronous programming significantly, making code more sequential, readable, and easier to reason about, even when dealing with complex parallel operations. This modern approach greatly enhances developer experience. Finally, let's be acutely aware of potential pitfalls and common challenges when working with TPL to ensure you can anticipate and mitigate them effectively in your projects. Understanding these helps in writing more resilient code. There can be inherent overhead associated with creating and managing tasks, which might negatively impact performance if not managed carefully, especially with a very large number of very small tasks. It's crucial to profile and optimize. Debugging parallel code can be significantly more complex than sequential code, as race conditions, deadlocks, and other concurrency issues may arise unexpectedly and be difficult to reproduce. Visual Studio's parallel debugging tools are invaluable here. Excessive parallelism can lead to thread starvation or contention, where threads spend more time waiting for resources than actually executing work, negatively affecting overall application performance. This highlights the importance of balancing task creation with available resources. By thoroughly understanding these aspects, including its benefits, features, and potential pitfalls, you can effectively harness the immense power of TPL in both your .NET and Unity projects, building highly performant and responsive applications. This knowledge empowers you to make informed design decisions. Thank you for joining us in this comprehensive exploration of the Task Parallel Library. We hope this guide has provided you with a solid foundation to begin your journey into parallel and concurrent programming. Happy coding, and may your applications always be performant.